Hello and welcome. In this worked example, we're taking a look at the question that you can see there on the screen. Two balls of masses m and 2m traveling in a vacuum with initial velocities 2v and v respectively collide with each other head-on as shown. After the collision, the ball of mass m rebounds to the left with velocity v. What is the loss of kinetic energy in the collision? Go ahead and do this working right here on the chalkboard. All right, so I've diagrammed the problem here. We've got the question, what is the loss of kinetic energy? And I've put sort of a before and after there. Let me go ahead. Try to get that. Plus it's you. All right. So we know that for a collision, we're going to use the principle of conservation of momentum. And so the first thing, like in any collision, momentum is conserved. We know that this is an inelastic collision. The question suggests it is because there's a loss of kinetic energy. If this were a perfectly elastic collision, then the answer to this question would be zero, right? So we sort of define a perfectly elastic collision as one where kinetic energy is conserved. But in any collision, inelastic or elastic, momentum is always conserved. It's one of the fundamental sort of laws of physics in the universe. Linear momentum is conserved. And so let's remind ourselves what that says. The initial momentum equals the final momentum. Here we've got the momentum of this object. So in general, momentum, it's mass times velocity, and we'll just have to sort of keep track of how much mass, how much velocity for each one of these objects. Keep in mind that velocity is a vector, and so whenever vectors oppose each other, we adopt a sign convention to make one negative relative to the other one. So the initial momentum is the sum of the individual momenta of all the particles. And so we'll start with this object here. It's got mass m and velocity 2v, so its momentum is, we can rewrite this 2mv, right? Move the coefficient in front, better form there. And then this one, you can see has the same momentum, right? So it's 2m for mass times v. But this time the velocity is sort of opposing it, right? So we'll sort of keep track of that. So we've got, the sum of the individual momenta. So we're always going to add the momentum of all of the particles, all the objects involved in the collision. It's the sum of the individual momenta. 2m, and here's where we introduce the negative sign, right? It's really the velocity that is negative. So it's times negative v, if you will, which effectively makes this term negative. And so we could say that 2mv minus 2mv, why that's zero. So the initial momentum is zero. The system has zero initial momentum. The momentum of each object sort of cancels each other out. And so the final momentum has to be zero. That's sort of what this is saying. The initial momentum has to equal the final momentum. Right? So if I sort of work through sort of the right side of that, considering the final momentum, knowing that the first mass here moves to the left with velocity v. So it was going at a speed of 2v, but it rebounds and it travels in the opposite direction at a speed of v. So what's its final momentum? We've already adopted the convention that left is negative, and so this one moving to the left is going to have final momentum negative mv. So then you ask yourself, what do I add to mv to make it zero? I'm sorry, what do I add to negative mv to make it zero? Indeed, positive mv. So whatever the momentum is of this object after the collision, it's equal to mv. We can't change the fact that it has a mass of 2m. It's like, so this sort of mv here is a 2m times some velocity, right, that's going to make it equal to this. And so you say, well, what velocity does that have to be? Well, if it's twice the mass, it's going to be half the velocity, right? So in other words, 2m times 1/2 v is mv, right? So we have negative mv plus mv is zero. We've conserved momentum like we have to in the universe, right? So this is always conserved. And now we know sort of everything about the particles. In fact, I'll sort of draw it out here. So now this object, which we can't change the fact that it's a mass of 2m, it's going to be traveling at a speed of 1/2 v, right? The question now asks us to calculate the loss in kinetic energy. So that's going to require us to consider the initial kinetic energy and the final kinetic energy, and then sort of take the difference between them. All right, we'll start with the initial kinetic energy. So that's sort of this situation here. We have the general equation for momentum. For good measure, let's put the general equation for kinetic energy, 1/2 mv squared. So the initial kinetic energy now, let's let's just sort of write it over here, right? So we'll say this thing has kinetic energy equal to 1/2, its mass is m, but its velocity is 2v, right? So you've got to square that. So that's the kinetic energy of this object. And while we're sort of working through, we could say 2 squared is 4. So we've got 4v squared times 1/2 m. So half of 4 is 2. We've got a kinetic energy here, 2mv squared, right? Because we have to square the 2 and the v. The kinetic energy of this object, now, kinetic energy is a scalar. So even though we have sort of a negative velocity this way, when we go to square, right, a negative times a negative is a positive. And so the kinetic energy, we sort of don't need to really worry about the negative sign too much here. So if I work through the kinetic energy of this object, it's going to be 1/2 the mass, which is 2m, times its velocity, which is v squared. Again, if you make it negative, that's fine. It's just going to become positive when you square. Half of 2 is 1, so we have mv squared, right? So the kinetic energy of this more massive object is mv squared. So this thing had 2mv squared. This thing had an initial kinetic energy of mv squared. And so the total initial kinetic energy is 2mv squared plus 1mv squared, or 3mv squared. So that's the initial kinetic energy. Both objects have a decrease in velocity. So this thing goes from 2v to v. This thing goes from v to 1/2 v. In order to preserve momentum, those must be the correct velocities. And so now we just have to sort of substitute those variables into the kinetic energy equation, similarly to how we did up here. So I'll just sort of this one here. This one just stays like the general form of the equation because it has mass m and velocity v. So 1/2 mv squared is its kinetic energy. This object is a little bit trickier. So it has kinetic energy equal to 1/2, but the m is 2m. 1/2 mv squared, but the v is 1/2 v. So we have 1/2 v, and that quantity is squared. All right. So if we sort of expand this, we're squaring sort of everything inside here. So 1 squared is 1, 2 squared is 4. We have 1/4 v squared times 1/2 of 2 is 1. So we have m times 1/4 v squared, which we could rewrite as 1/4 mv squared. Right, so we've got the kinetic energy of this object, 1/2 mv squared. The kinetic energy of this object after the collision, 1/4 mv squared. So we've got 1/2 mv squared plus 1/4 mv squared. 1/2 is the same thing as 2/4 mv squared plus 1/4 mv squared. And so we've got 3/4 mv squared. Does not equal the 3 mv squared that we started with, right? So we've shown that if this were a perfectly elastic collision, these things would be equal. The question suggests that it's not perfectly elastic, right? There is a loss in kinetic energy. So we sort of say, well, yep, they're not equal. We didn't expect that they would be. We need to take their difference to get the loss, right? So 3/4 is less than 3, but by how much? So 2 1/4 mv squared is the missing kinetic energy. Mixed number, 2 1/4. You may recall that you multiply the denominator by the whole number and then add the numerator to convert a mixed number to an improper fraction. So this one will become 9/4 mv squared is what we expect the loss in kinetic energy to be. Let's consult our answer choices once again. And indeed, choice C, 9/4 mv squared, is the best answer that we could come up with, but for even to be even more thorough, let's go ahead and cue up the mark scheme. This is question number 10 from this paper. This came from paper 1 in 2019. And so question 10 is indeed choice C. So we give ourselves that positive feedback. This has been another worked example with Dr. Schleich, still living the physics life. We'll see you shortly for the next one.